given by Štefan Gyürki, and this lecture is titled as Coherent Configuration and Association Scheme.
Thank you very much, Jelena, for the introduction. Today we will move from permutation groups to a kind of abstract algebra, and after that we will come back to combinatorics, so it will be a quite natural way to continue. And today I will try a little bit different software for presenting, so I'm sorry, I would like to write on the slides in nicer manner than in previous lectures, so I need to switch off my camera and to switch my screen. So now if everything is visible, then we can continue. I hope that nothing had happened when I changed the screen. Okay, so we were talking about permutation groups for 2-3 weeks. May I ask somebody? Yes?
It seems to me that it is noisy a little bit. I don't know why.
One reason can be that somebody is having its microphone on.
No. It was from your microphone. Now it is better.
Okay, maybe I have just to take less volume. And I get also a message that my internet connection is unstable, so maybe these two things in common made some problems, but
I see now everything is fine.
Okay. Okay, so let's continue, or let's start. First, we would like to move from permutation groups to algebras, and one way how to do this is using matrices. To each permutation, we can assign a matrix which is simulating what the permutation is doing. For example, if I am taking a permutation 1, 2, 3, then to this permutation I can assign a matrix which will tell me that I am moving element 1 to element 2. So in the first row and second column I put 1, and to other places 0. In the second row and third column I put 1 because 2 is moved to 3 and 3 is moved to 1. I put 1 to the third row and the first column. So I can define like this a permutation matrix. It is easy to see that composition of permutations are in accordance with the matrix multiplication, and also it is easy to see that since a permutation is a bijection, then in each row and each column we will have exactly 1, and other entries are zeros. Also, if I have a fixed point, then I have 1 on the diagonal, so the sum of the entries on the diagonal, that is the trace of the matrix, is the number of fixed points of the permutation which we were denoting by chi of G. Third basic property is that the determinant of such a matrix is either +1 or -1. This can be easily obtained by usual expansion of matrix when computing determinants. I think this is Laplace expansion, and moreover, the determinant is +1 if and only if G is an even permutation. Again, it is a very easy exercise to prove that this happens. It is enough to know the basic properties of the determinants. And also, it is very easy observation to see that the inverse permutation has a permutation matrix which is transposed to the permutation matrix of the original permutation. And now we can also obtain matrices from graphs simply by assigning to a graph the adjacency matrix. I think this is already known for everybody. For example, if I have say this graph, then I can say by my matrix that the vertex 1 is joined to vertices 2 and 3. So each row and each column corresponds to a vertex of a graph. And I am putting 1 if there is a dart from I to j. So from the vertex 1, there is dart to vertices 2 and 3. From vertex 2, there is dart to 3 and no other darts. And from vertex 3, I have dart to the second one and no other. So this is how the adjacency matrix looks like for this concrete graph gamma. So it is basic concepts from graph theory, but here we can repeat it because we will do a lot of job using matrices. And also, of course, if we have an undirected graph, then the adjacency matrix is symmetric because there is darts from I to j and j to I. Now, we will join these two things in such a manner that I can define for each dart ij a matrix which is containing in the ith row and jth column 1, and all other entries are zeros. Now, if I am taking a permutation G and we'll do this multiplication with this matrix, then I will obtain matrix which has 1 in the kth row and lth column, where k is the image of I under permutation G and L is the image of J under the permutation G. So it looks like some conjugation, but if you will honestly do the matrix multiplication, you will obtain that this really works. Now, if you will do the same job for an adjacency matrix of a graph gamma, then of course you are mapping by permutation G the full graph gamma. So you will obtain an adjacency matrix of a new graph in a sense that the labels are, or the vertices are mapped by the permutation G. Now, we can, by this multiplication, recognize the automorphisms of graphs, simply because if G is an automorphism, then these two adjacency matrices are the same. So this works if G is an automorphism of the graph gamma. So we can say that G is an automorphism of the graph gamma if and only if this equation holds. And equivalently, we can say that the permutation matrix of G commutes with the adjacency matrix of the graph if and only if G is an automorphism of the graph gamma. So this is very important knowledge, because just using the matrices we can precisely characterize the automorphisms of a graph. So let us take an example. The graph gamma here is the complete bipartite graph K22, and from the adjacency matrix I can say that it was labeled precisely like this. And if I am considering the permutation G, which interchanges 1 and 2 and 3 and 4, then if I will count the matrix A times M and M times A, then in both cases I am obtaining the same matrix, and this is saying to me that this permutation is an automorphism of the graph gamma. And if I check this on the picture, 1 is going to 2, 2 is going to 1, 3 is going to 4, 4 is going to 3, then really 1, 2 is an edge, 1, 4 is an edge here now on the image, and so on. I can honestly check that this really works. Now, so this is a way how to switch to the language of matrices from permutations and from graphs. And maybe it is interesting to ask the opposite question, that if I am given a permutation group, then what is the set of all matrices which are commuting with each permutation matrix corresponding to the permutations of the given permutation groups? So I can collect all the matrices of dimension n by n, where n is the degree of the permutation group, and I can do this job, say, about a field F, but also often it happens that it is sufficient to work with over the ring of integers. So there are not really no restriction in this direction that F should be a field, but this is, I think, natural to consider a matrix over a field. And we will collect all the matrices over such field F which have this property that they are commuting with each permutation matrix corresponding to permutations of the permutation group G omega. And this set is called the centralizer algebra of a permutation group G omega. It is not so hard to check that this algebra is a matrix algebra. One has to check that if two matrices are belonging to this algebra V, and if we are taking any scalar from the field F, then we have to check that the product of matrices A and B belongs also to this algebra. For example, we can check this. It's an easy exercise. So if A and B are in V, this means that A commutes with mg for each G, also B commutes with mg for each G. So now we would like to check that AB is also commuting with mg. So step by step, it is easy to check that, for example, B is commuting with mg, so I can write this in this manner, and also A is commuting with M, so I can prove that really the product of two matrices is also belonging to the centralizer algebra if the two matrices are belonging to it. Similarly, it is easy to check that the sum of two matrices from the centralizer algebra is also from the centralizer algebra, and also a scalar multiple of any matrix belongs to that. If we have the centralizer algebra, then we can say that its dimension is precisely the number of two orbits of the permutation group. And since this number plays an important role, then we will call this number as a rank of a permutation group. So it is the number of two orbits of the given permutation group. And also, if we will take the adjacency matrices of the basic graphs, or adjacency matrices of the relations which are formed by the two orbits, then we are obtaining a basis for this algebra, and this basis is called the first standard basis. And we write that the centralizer algebra V is generated by matrices A1, A2, and so on, A3. So we will refer to the two orbits as basic relations, and for the corresponding graphs as basic graphs of the centralizer ring. So similar concepts like what were in the previous lectures. A little bit later, and I will give also examples for this. Now we know that the product of two matrices from the algebra are belonging to that algebra. So that means that if I am taking, for example, product of two basis matrices AI and AG, then I can write this product as a linear combination of the matrices from the basis. So there exist constants Pij, such that AI times AG is these constants times first matrix and so on and so on. It's important to warn everybody that this constant has to be read that this is a superscript, not a power. These structure constants have three indices because they are really depending on I, on J, and on K. So we are obtaining a tensor which is three-dimensional, and we will call this tensor as a tensor of structure constants of the centralizer algebra. First thing which has to be noticed also is that all these constants are non-negative integers. This is because AY and AG are 0-1 matrices, and if I am multiplying two such matrices, then this product is clearly non-negative because I cannot create any entry which will be negative. And on the other hand, if I write this as a linear combination of 0-1 matrices, then of course these matrices AI, AG are such that precisely one of them has a concrete entry as one, all others having on the same place zeros, because they are corresponding to two orbits, and each pair appears in precisely one of the two orbits. So if I have, for example, ST entry some number in the product AI-AG, then it appears on the same place, appears one in just one matrix, say K, and in all others are non-zeros. And that entry should be non-negative. That means that the coefficient in the corresponding matrix will be also non-negative. Oh, I'm sorry, I'm giving all the definitions in a row, but after that there will be more examples, so please be a little bit patient in this. So let's switch to the language of graphs a little bit. To each basic relations we can form the basic graph, and we will denote them gamma 1 up to gamma r. And we know that these graphs form a partition of the second Cartesian power of the ground set omega. And we can now assign a color I to to the ith basic graph and color the corresponding arc with this color. In this manner, we can assign to each dart of the complete graph with loops one color. For example, the complete graph on 3 vertices look like this with loops. And this means that since each pair belongs to some of the 2 orbits, I will assign to the corresponding dart the color of that 2 orbit. So in this manner, I can obtain a complete color graph, or if I will play the same game with matrices, then I can obtain so-called generalized adjacency matrix, which corresponds to the complete color graph. I will switch the next slide and I will come back because really this will be much easier to understand on examples. So for example, if I have the permutation group, which is generated by these 2 elements, then this permutation group has 3 2 orbits. One of them is the diagonal orbit, so it contains the pairs 1, 1, 2, 2, 3, 3, 4, 4. The second has pairs 1, 2, 1, 4, 2, 1, 2, 3, and so on. So you can read the full information from the adjacency matrix of the corresponding 2 orbit. And also we have a third 2 orbit, which is formed by these pairs. Now to each 2 orbit, I assigned a color. I said that the first 2 orbit will be red, the second will be green, and the third will be blue. Since this forms a partition of the complete binary relation on over the set omega, then I can write the generalized adjacency matrix in this form, that all those entries which are corresponding to the first 2 orbit will be assigned to the color 1, which in this case is the red color. But even if I will forget about colors and will use just numbers, it will be clear that entries which are ones are corresponding to the first orbit. Also, the entries which are twos are corresponding to the second 2 orbit, and here we have the pairs from the third 2 orbit. So in this manner, instead of using, say, 3 matrices, we can display the full information which are contained in the 2 orbits just simply by using one matrix. And the similar thing can be done with graphs. and 4, 4. So here in the picture, they are by red color. The darts corresponding to the second orbit were displayed with using green color, and the darts corresponding to the third orbit are displayed by blue color. So again, from this picture, it is clear how the two orbits of the permutation group looks like. I hope it is clear that I can, to each permutation group assign such a generalized adjacency matrix and also this kind of complete color graph. Now let's go back to the slide I skipped. If we understand what the complete color graph is doing, then it will be easier to understand the complete the combinatorial interpretation of the structure constants, because if I have two vertices S and T, and the dart between the structure constants, which I denoted by Pijk, is precisely the number of walks of length 2 between S and T, such that the first dart is of color I and the second dart is of color J. So it counts how many X I have, such that this triangle here will be precisely in these colors. So this is a combinatorial interpretation of structure constants. So they have very nice combinatorial meaning. Now, if we return to our example, then of course we can count the products of basic matrices. A1 is clearly the identity, so it is easy to multiply with the A1. And an interesting thing we are obtaining when we are multiplying A2 by A2, we are obtaining that it is twice A1 plus twice A3. And that means that, for example, the structure constant P221 is equal to 2, and also this one is equal to 2. And now, if we know the combinatorial interpretation of structure constants, then we can say that, for example, P22 superscript 3 equals 2 means that if I have an arc of color 3, which was the blue one, then there are two such triangles where both sides are of color green in this order. And if I take a look on the complete color graph I obtained from the permutation group, then I really see that, for example, over this green blue dart, I have one triangle and I have the second triangle, which has the remaining sides in green color. So I can tell the structure constants, for example, from this picture, because it is quite small and I can easily track all the volts of length too. Okay, so these are centralizer algebras and structure constants, and one can now ask the question, okay, I obtained nice algebraic structure from a permutation group, but what if I forget about the permutation groups, and I will just ask that similar properties are required from matrix algebra. And the answer for this is positive, because in matrix algebras we really have such a structure which carries these properties, and this concept is called coherent algebra, and it is more, it's a little bit more general than the concept of the centralizer algebra. So let us take matrix algebra over the field of complex numbers, and we will require that this algebra has a basis from 0, 1 matrices. So this is axiom 1. And also we require that the sum of all basic matrices is the full one matrix. So this means that, for example, J3 is the matrix which has just one S entries. And the third requirement is that if I have in the base a matrix A, then its transpose should be also in the matrix algebra. This is corresponding to the requirement that if I have a 2 orbit, then also its transpose relation is 2 orbit. So now it is translated purely into the language of matrices. So to require this property, I need that with each matrix, its transpose matrix will be also inside the matrix algebra. And the fourth requirement is that the identity matrix should belong to this algebra. And if all these requirements are fine, then we are speaking about a coherent algebra with standard basis consisting of matrices A1, A2, and so on, A3. And similarly, we can write that the matrix algebra W is generated by matrices A1, A2, and so on, AR. And we can make a step towards the combinatorial language or relational language. And in similar manner, we can define a combinatorial object which is called coherent configuration. Here we require that we have a collection of binary relations on a ground set, say X. And we require that two binary relations are disjoint if I'm making the intersections of two different binary relations from the collections, and the union of all binary relations from the collection is covering the full second Cartesian power of the set X. This means, in other words, that R is a partition of the second Cartesian power of X. And similarly, we require that with each relation, its transposed relation will be a part of the collection R. And the fourth requirement is that I can create the full diagonal relation as a union of some of the relations from the R. And the last requirement are saying exactly that V has to have structure constants. That is, if I am taking X Z of, I'm sorry, just to be in accordance with the notation in the fifth axiom, if I am taking a pair XY in RK, then the number of Z's such that the pair XZ is from Ri and Zy is from Rj is constant, which is not depending on the concrete choice of the pair from the relation Rk. It depends just on the chosen three binary relations Ij and Ra, Rj, and Rk. So in combinatorics, the analogous object is called coherent configuration. So now we can switch from one language to other. We can formulate similar things in the language of matrices, in the language of relations, and in the language of graphs. And this is quite useful because we can switch if something can be expressed better in the language, for example, matrices than in the language of graphs and so on. So a few remarks about the definitions. If we have a coherent configuration, then of course the adjacency matrices of the relations are generating a coherent algebra. Simply, it is easy to see from the axioms. The correspondence between axioms 1 up to 4 is easy to see, and the fifth axiom of the coherent configuration just says that each product AI AG should be a linear combination of the basic matrices I1 up to IR. So this was how to say that in the terms of relations, that the corresponding matrices are forming a matrix algebra. Now, we already seen that from permutation groups we are obtaining coherent algebras, and of course from permutation groups similarly we can obtain coherent configurations. But these are not all coherent algebras or coherent configurations. So those which are coming from the permutation groups exactly in this manner that we are creating two orbits of the permutation group are called Schurian coherent configurations. And if they are not coming in this fashion, those are called non-Schurian. Just maybe a small remark, the smallest case where exists a non-Schurian coherent configuration, it appears on 14 points. So it is not so small that I can now show you and give a full picture, but I would like to say that such non-Schurian coherent configurations do exist. Okay, so now again a few examples in order to understand the definitions. So take a permutation group, which is in fact the cyclic group of order 3, but take it in such manner that the point 1 is always fixed. This permutation group has 6 two orbits. So I can write the set of two orbits here. This means that these two orbits correspond to Schurian coherent configuration. And the same thing I can say in the language of matrices simply by showing all the adjacency matrices of the corresponding relations. Pardon. And also I can say the full information using the language of graphs. So the graph gamma 1 says that it contains the pair 1, 1 and nothing else. The graph gamma 2 says that it contains the pairs 2, 2, 3, 3, 4, 4 and nothing else, and so on. So you can see the correspondence between relations, adjacency matrices, and also adjacency matrices and graphs, etc. And the generalized chord matrix corresponding to this coherent configuration looks like this. So I don't think that we have time to check, but this really works and you can check it at any moment. Now, there are more properties of the coherent algebras. If we take two square matrices of order n, then we can define a product which is called in the literature Schur-Hadamard product of A and B, and this is precisely that matrix product which many students would like to prefer in matrix when teaching matrix multiplication, because it is defined precisely that I obtain the element which is in first row and first column by multiplying the corresponding elements from the first matrix and the second matrix. Also 4 times 6 here is 24 and so on. So this product is called Schur-Hadamard product. And it is easy to understand how does it work. And an important property of the coherent algebras is that each coherent algebra is closed under this Schur-Hadamard multiplication. This is easy to verify because you need just to verify it on the matrices from the basis, and these matrices are 0, 1 matrices, so you can easily see that if you are multiplying the basic matrix with itself, then you are obtaining the same matrix because you are multiplying 0 with 0 and 1 by 1 with 1. So it is natural. And if you are multiplying different matrices from the basis, then you are obtaining the full zero matrix because precisely, or at least one of those two matrices having 0 in each entry. So this is easy to check, and here we have an important Schur-Wieland principle which says that if you have a matrix X from the coherent algebra W, then you can make something like a cross-section, which is called cross-section. This means that, for example, if you are choosing the number, say, 2, then the cross-section of the matrix X by value 2 is the matrix which you obtain in such manner that you keep all the entries with the same value which are equal to the chosen value, and all others will be 0. And this principle says that if you do this cross-section, then this matrix belongs also to the coherent algebra. One way how to see this is just to
Štefan,
check
could
that.
you please demonstrate the previous slide one more moment?
Yes. Okay.
Yes, okay.
So one way you have to see this is just to take the matrix and choose for the chosen value. If there is no such value in your matrix X, then of course the cross-section will be the 0 matrix, and this belongs to the coherent algebra. Otherwise, you can find an entry which is equal to the chosen value, and to take the basic matrix AK1, which have exactly on that place entry 1. We know that there is precisely one such matrix and all others have on the same place 0. So we can create a new matrix which will eliminate this entry and also all the other entries which which are on the place where this matrix AK1 having the entry 1. So, but step by step, we can decrease the number of these entries which are having the chosen value, and in finite number of steps, we will come to an end. And maybe it is much easier to prove this just by simply writing the original matrix as a linear combination of the basic matrices, and after that to see that the corresponding coefficient should be equal to the chosen value in all, besides all those matrices which are having ones on the places which are occupied by the chosen value ni. So if we will do this job, then immediately one can see that, of course, there is a collection of basic matrices which was some covers the places which were covered by the value ni. So this means that there is a collection of basis matrices such that they should have a linear coefficient or coefficient in the linear combination equals to the value nu, and we will obtain the matrix or the cross section of matrix Y on this value, on this chosen value. In fact, this is much easier if you will write down and to see what is going on. And why we are doing all this job is simply have to recognize a coherent algebra from the other side. I mean that we know that the subspace of the matrix algebra over the complex field is a coherent algebra if and only if it contains the identity matrix, the all one matrix, it is closed under the usual matrix multiplication, it is closed also under the Schur-Hadamard multiplication, and it is also closed under the transposition, conjugate transposition, when we are working with complex field. So this is a sufficient condition for checking whether a matrix algebra is forming a coherent algebra. And one can define the coherent subalgebra of an algebra. This simply defined like almost any substructures in algebra, that H1 should be a subset of H2, and all the axioms for coherent algebra should be preserved. So this is a coherent subalgebra, and it will be important for the next lecture that if we have two coherent algebras of the same order, then their intersection is also a coherent algebra. But this, we will go into this direction in 2 weeks. And the most important thing in the next lecture will be the smallest coherent algebra which contains a chosen matrix. We will see that this is really a coherent algebra, and it is obtained as an intersection of all coherent algebras which are containing this chosen matrix M. So for today, we will stop going in this direction, and we will continue with the association schemes. I will return back to this in 2 weeks. So this smallest coherent algebra, which is containing the matrix M, is called coherent closure, and it is also interesting when you have not a single matrix but a set of matrices. So everything works perfectly, and we will see it on the next lecture. But now let's continue with the combinatorial object, which is called an association scheme. We have already seen coherent configurations, and the association scheme is a homogeneous coherent configuration. This means that the full diagonal relation is contained in the collection of relation as one relation. So now it is not allowed to have it as a union of two orbits or a union of binary relations, but it is appearing as a single relation. This means that if we consider, for example, Schurian association scheme, that it is coming from a transitive permutation group. A coherent algebra, which is corresponding to an association scheme, will be called adjacency algebra. And if an association scheme has all relations such that they are self-transposed, that is, the relations are symmetric, or equivalently saying that all the basic graphs are undirected, then we are speaking about a symmetric association scheme. And if the corresponding adjacency algebra is commutative, then we are saying that the association scheme is commutative. This happens precisely when, for all structure constants, we have that Pijk is the same number as Pjik. So this is commutativity of association schemes, and in such a case, we will call the corresponding adjacency algebra as Bose-Messner algebra, or shortly BM algebra. And it is easy to see that whenever we have a symmetric association scheme, then this association scheme should be also commutative. Its proof is just a simple playing with matrix multiplication. So we can write the product AY-AG as a linear combination using structure constants. Now, if we consider the transposition of this product, then from the transposition of multiplication, we obtain the first step. And since our association scheme is symmetric, then the matrices from the basis are also symmetric. So this is the same as transposition. And we know that AJ, AY can be written as linear combination of the basic matrices. On the other hand, from this equation, we are obtaining that its transpose can be written like this, and simply using the properties of transposition and working with matrices, we obtain that these two things are equal. Since we have a basis from the matrices A, K, or they are forming a basis, then of course the two linear combination should have the same coefficients, and from that we are obtaining that really for each structure constant P, I, J, K, it holds that it is equal to P, J, I, K. So the association scheme is commutative. So also association schemes are fully given if I am saying, for example, what is the permutation group that is coming from, or by giving pictures of basic relations. So for example, if here we consider the dihedral group on 6 elements, that is dihedral group of order 12 and the degree 6, then its non-diagonal two orbits look like this. So from the pictures we can see that this association scheme is symmetric because all of the basic graphs are undirected. So here we have an example of a symmetric association scheme. So thanks to previous proposition, we know also that, of course, this symmetric association scheme will be also commutative. In the next example, we have a permutation group which is non-symmetric but still commutative. It is non-symmetric because, for example, the basic graphs gamma 1 and gamma 2 are directed graphs. And in order to see the commutativity, it will need some effort to check that the structure constants are the same whenever we switch I and J. So you can do it as homework. And let us consider a little bit more complicated example. We can represent the symmetric group on 3 elements in usual way, but now I was not using symbols 1, 2, 3, I was using instead of them V1, V2, and VT in order to indicate the vertices of a graph which is on the figure. And I can consider the action of this group on the set of darts. And I will use symbols 1, 2, up to 6 for the darts. So the first generator of the group, which is interchanging vertices V1 and V2, is generating or inducing a permutation of the darts, which can be written like this. So the dart 1 will be interchanged with dart 2, 3 goes to 5, 5 goes to 3, and 4 and 6 will be also transposed. And the second generator, which cyclically interchanges vertices V1, V2, and V3, of course, it maps 1 to 5, 5 to 6, and 6 back to 1, and 2 to 4, 4 to 3, and 3 to 2. So it is easy to check that this is really the induced permutation on the set of darts. This is a non-commutative group. This is the smallest group which is non-commutative. And we now took its action of degree 6. So I can consider a permutation group G on 6 points, which will be generated precisely by these generators. And to see the Schurian association scheme corresponding to this group, I can write the pictures or the diagrams of the basic graphs. Here, there are missing two basic graphs. One is the basic graph corresponding to the loops or to the diagonal relation or to orbit. And you can imagine the last two orbits simply by reversing the darts of the graph gamma 5. So here we see that, in fact, gamma 2, gamma 3, and gamma 4 are undirected graphs, but gamma 5 is directed, and therefore I gamma 6, what is its reverse digraph, directed. So clearly this association scheme is not symmetric, and for example, we can check that also it is not commutative. If I will consider just colors 2, 3, and 5, that is colors red, green, and yellow on the previous picture, and just to consider one picture, then I can check that the structure constant P235 is equal to 1, because if I select, for example, the yellow dart 6, 1, then I would like to count the number of triangles or two walls going from 6 to 1, which have the first dart in red color and the second dart in green color. So here I have one such triangle, and there are no others because there is no other red dart going out from the vertex 6. So I can check that this constant is equal to 1. And if I am counting the structure constant P3 to 5, then first I would like to go out from the vertex 6 along the green dart. So this is the only possibility, but from vertex number 4, there is no dart going to 1 in red color, so this constant will be 0. So P2, 3, 5 is not equal to P3 to 5. Therefore, the association scheme is not commutative. So this example I used to show you an association scheme which is not commutative. Now let's go to the properties of the structure constants. I will show you 8 identities concerning them. First is saying that if you are counting such a sum and this sum, then these two values are equal. How to see this? In order to see this, one has to realize that both these sums are counting the walks of length 3 between two vertices and with chosen colors I, J, L. So say I have dart A, B in color K, then if I would like to count the number of walks of length 3 which have colors I, J, and L in this order, then I can count these numbers. For example, I will first count how many this dart is in L over K. And after that, I can ask what is the number of two walks from A to this vertex which have colors I and J, and of course this is independent of the choice of S, so it is P, I, J, S, and I am accepting all S's which came into account, so I am summing through S from 0 to all possible colors. And I can play the same game in other way, that first I will count the number of such vertices that from A to B I can go on 2 steps using color I, and after that using any color T. And similarly as here, I will after that count the number of triangles over the color T where the first dart is of color J and second is of color L. So by this reasoning, I can easily obtain that this identity is really valid. The second identity is a little bit easier. If I am denoting the valency of the basic graph as Ni, then of course the valency of the basic graph gamma I is the same as the valency of the basic graph, which is the reverse of the same graph, because the basic graphs are all regular. So the number of incoming darts is the same as outgoing darts from one vertex, and if I am making the reverse, then the same will be valid. So this is, I think, the easiest identity. After that, we can obtain an identity like this, and this simply works because if you multiply a matrix which has the same number of ones in each row and each column, and if you multiply them with the all one matrix, then of course you are in each entry obtain the precise number of ones in each row and each column. So for example, if we have, say, this matrix and you multiply from one or other side with this matrix, then of course you obtain everywhere 2's, because in each row you have 2 1's, and if you multiply from the other side, then you obtain again 2's, because in each column you have precisely 2 entries which are equal to 1 and the others are zeros. So this equation is appearing quite often when you are working with regular graphs, so it is good to remember. And the identity tree is one of its consequences. Now, identity 4 says that if you count the sum of such intersection numbers where the first subscript and the superscript are fixed, then you are obtaining the valency of the basic graph K. Why it is? Because if you are choosing say a pair which is joined by color J, and if you are choosing a color K, then there are nk darts going out from these vertex and of color K, and since you have a complete colored graph, then from each such vertex, there is some I which sends you to the end vertex of the chosen dart. And similar game can be played also if you fix the incoming colors. So again, from each such vertex, there is precisely one color for each of them that completes this picture into a triangle. And the second formula is easy to see, because if you count the number of darts outgoing from a chosen vertex, then of course each dart is at some place counted, and since we have also a loop, then from each vertex there are n darts going out, and this means that if you sum the valencies of the basic graph, you are obtaining the number of vertices. Now my time is slightly running out, but still I would like to show you at least an outline of the proof of the next identity. The next identity shows that the sum of structure constants Pijs multiplied with the valency of the basic graph S gives you the product of valencies of the ith and jth basic graph. This simply holds because if you choose colors I and j, these are fixed in the sum, then you can simply count from a fixed vertex, say A, that how many vertices can be reached exactly using these two walks. And each such picture can be, of course, completed by one dart of some color S. So if you count these, then there are ny by nj vertices reachable in this manner. And on the other hand, you can count over each color S, how many pictures like this do you have? So again, it is not the easiest thing, but if not the hardest. If you understand what the symbols are meaning and you will write a picture, then you will obtain everything. Now, I will leave the next three identities as a homework. Identity 6 is quite easy. It is saying just what is going on if you consider what is going on around a loop. The identity 7 says that what is going on if you just simply transpose the picture. And identity 8 is a little bit more complicated, but hint will be given. So let me continue with some theoretical things. Similarly, the concept of primitivity can be extended also for the association schemes, giving by the same definition. We will call an association scheme primitive if each of the basic graph corresponding to that association scheme is a strongly connected graph or digraph. And otherwise, the association scheme is called imprimitive. So immediately from this definition, it follows that if we start with a primitive permutation group and we will create its two orbits, then we are, of course, on one hand are obtaining an association scheme, and since they will share the same two orbits or the same basic relations, then the association scheme is primitive. So this is quite direct consequence of the concept of primitivity. In example, I will show that if you consider the cyclic group of order P, so that P is cyclic group of order P, where P is a prime number, then each of the non-diagonal two orbits will be connected. That means that the corresponding association scheme is primitive. The picture is showing what's going on when the prime number P is equal to 5. In the last series of homework, I was giving you a task in order to show that the similar thing happens when you are considering the dihedral group. So if we can extend primitivity for association schemes, then we can say that the strongly regular graph is primitive if corresponding primitive, if the corresponding association scheme is primitive. What a strongly regular. In fact, the strongly regular graph defines the association scheme with rank 3 or 2. This means that going j and k, running j and k between 1 and n. So you are obtaining n by n matrices where n is the number of points in the association scheme. So here is an example, a very easy example, such that here you have P0, 0, 0. This is this one from here. After that, you have this from here, and so on. So here you are collecting the structure constants which have first subscript 0. And into B1, you are collecting the structure constants which have first subscript 1. And what is interesting and useful, that these matrices again form an algebra, and this new algebra is isomorphic to the original adjacency algebra. And the isomorphism is given in very similar manner, that the matrix IA is sent to the matrix BI. In general case, the two things are not isomorphic but anti-isomorphic, meaning that phi AB is phi B times phi A. So this is an anti-isomorphism. So phi is bijective, and for each AB this holds. Of course, if the algebra is commutative, then you can switch these and you are obtaining isomorphism. That was the reason that in the previous example we had the isomorphism. So if you consider the algebra, the usual algebra corresponding scheme, and it is enough to work with product of matrices and to expand the obtained expressions. So on one hand, you are obtaining this, and from this you can immediately see that how to choose.
Stefan, could you please demonstrate the statement of theorem one more moment?
Sorry?
The theorem, yeah.
To demonstrate?
Thank you, thank you.
On example or just to show it?
The statement of theorem.
Mm-hmm. Here.
Thank you.
Okay. So the intersection algebra and the adjacency algebra are anti-isomorphic. And we know how the anti-isomorphism looks like. And moreover, we know that the basic matrices and the intersection matrices are sharing the minimal polynomials. So I think I have to finish slowly. So this is again just a simple exercise in linear algebra to prove that this really works. And as I was already referring to it, then this new algebra is called intersection algebra. And when the original adjacency algebra is commutative, then the anti-isomorphisms is switching to a usual isomorphism. And I think the remarks are not so important for now. So thank you for your attention, and I think I was using more than 100 minutes again. I'm sorry for that.
Thank you very much for this very interesting and nice talk and lecture. And actually, it is very important to give a lot of examples and a lot of basics, especially for this new series. So it was really very nice. Thank you very much.
Mm-hmm.
And now, are there any questions to Štefan? Well, we had some questions during your talk, so I think that now we can stop here. And one more time, let me say you again, thank you very much, because it is very important to have a lot of explanation, especially when you give so many new definitions. So please don't worry about your time. So time is time, and we have enough time for basics. Yeah. Well, okay. Štefan, thank you very much.
You're welcome.
Do you have the list of exercises for homework, or it will be enough to consider some of your statements within this lecture?
Yes, I prepared 3 exercises, but after this lecture, maybe I will extend the list by some.
Okay.
So
Okay. Okay.
I will send it to you in, say, 2 days.
Exactly. Yeah. Right. Yes. Thank you very much. So, and after that, we will put your presentation and the list of exercises on the webpage so that they will be available for all of our participants. Okay.
Štefan, Elena, what about the next problem solving? Is it possible to have problem solving after next Ural seminar on group theory and combinatorics?
Yes, of course, it will be possible.
A small announcement.